In this presentation, we'll explore the types of batteries lead-acid and lithium-ion. We'll break down their components, understand how each part contributes to energy storage and delivery, and examine how these elements scale from individual cells to full battery systems. Batteries come in many forms, each with unique chemistries, structures, and performance characteristics. From traditional lead-acid and nickel-cadmium cells to advanced lithium-ion, solid-state, and flow batteries, every type is designed to meet specific needs. In this module, we will explore their structures, advantages, limitations, and applications, and see how technological evolution is shaping the future of energy storage. On the market today, you can find a wide range of battery technologies, each designed for different applications. Lead-acid batteries remain one of the oldest and most cost-effective solutions, while VRLA batteries are sealed and maintenance-free. Nickel-based technologies, such as nickel-cadmium and nickel metal hydride, have long been used in tools, aviation, and hybrid cars. Modern solutions like lithium-ion batteries dominate electronics and electric vehicles due to their high energy density. At the same time, next-generation technologies such as solid-state, flow, and sodium-ion batteries are gaining momentum, particularly for grid-scale and renewable energy applications. Together, these technologies form a diverse landscape of energy storage solutions. Lead-acid battery technologies vary significantly based on their chemical composition and intended applications. Lead-acid batteries, despite being an older technology, remain incredibly relevant. They are considered one of the most cost-effective and widely used battery types, offering high capacity per unit cost, a long lifespan, and an impressive recycling rate of up to 99%. This efficiency and widespread availability make them a cornerstone in many industries. We will divide our discussion into two main categories: flooded lead-acid batteries and the more modern valve-regulated lead-acid, or VRLA, types. Let's begin with flooded lead-acid batteries, also known as wet cells. These batteries typically contain a liquid electrolyte and are characterized by having numerous, though thinner, plates, which generally results in a lower number of charge-discharge cycles. Within this category, we have starter batteries, or SLI batteries, which are the familiar car batteries used in vehicles, marine crafts, and generators. They come in various voltage ratings to suit different applications. Then we have industrial batteries, which are designed for more demanding, long-term use. This group includes stationary batteries, crucial for standby power in critical infrastructure like UPS systems for data centers, communication networks, and hospitals. They also serve as primary power sources in remote, off-grid locations, leveraging renewable energy sources. Industrial traction batteries are designed for heavy-duty applications such as forklifts, airport vehicles, cleaning machines, and mining locomotives. These batteries are ideal in places where emissions and noise are undesirable and where explosion risks exist, such as underground environments. They usually have a lifespan of more than 5 years. Most traction batteries are made by assembling multiple 2-volt cells into large steel cases, connected with lead bridges or cables. They come in capacities ranging from 150 ampere-hours up to 1500 ampere-hours, with voltages from 12 to 96 volts. Their weight can range from 500 kilograms to several tons. With cycle lives exceeding 1500 for wet cells, traction batteries remain an indispensable energy source in industry. Valve-regulated lead-acid batteries, known as VRLA, include AGM and gel types. These are sealed batteries that prevent leakage and require no maintenance. They are safer, more versatile, and can operate in any orientation, whether upright or sideways. VRLA batteries also produce minimal gas, have a longer shelf life, and resist vibration, making them easy to ship and transport. They are commonly found in caravans, recreational vehicles, mobility scooters, and renewable energy systems, where safety and reliability are critical. In AGM, or absorbed glass mat batteries, the electrolyte is fully absorbed into glass fiber mats, so there is no risk of leakage, even if the case is damaged. AGM batteries are known for their high efficiency in both charging and discharging, and they perform well in deep discharge applications. Gel batteries, on the other hand, use silica to create a gel-like electrolyte. This prevents leakage, even if the casing is broken. They operate with lower charging voltages and are very sensitive to overcharging, but they are ideal for deep cycling and hot environments. Both AGM and gel technologies represent advancements that make lead-acid batteries safer and more adaptable. VRLA technology represents an important step in the evolution of battery design. By sealing the electrolyte inside, engineers reduced the risk of leakage, minimized gas emissions, and eliminated the need for regular maintenance. This design makes VRLA batteries safer and more versatile compared to traditional flooded lead-acid batteries. They can be mounted in any orientation, which is very useful in confined spaces. Because of their safety and reliability, VRLA batteries are widely used in telecommunication systems, renewable energy setups such as solar and wind installations, recreational vehicles, and medical equipment. Their adaptability shows how battery design continues to evolve to meet modern energy storage challenges. Lithium-ion batteries have become the backbone of modern energy storage. They are lighter, more compact, and offer much higher energy density compared to older technologies. Lithium-ion cells provide safe and reliable operation across a wide temperature range, typically from -30 to +60 degrees Celsius. They also have excellent charge and discharge performance, low self-discharge, and can store a large amount of energy in small, lightweight cells. This combination of features makes lithium-ion the dominant choice for electric vehicles, smartphones, laptops, uninterruptible power supplies, and even large-scale renewable energy storage. They represent the cutting edge of today's battery technology. One of the strengths of lithium-ion technology is its diversity. By adjusting the materials used for the anode and cathode, as well as the physical shape of the cell, manufacturers can optimize batteries for different applications. On the anode side, graphite is the most common choice, being inexpensive and widely available. Alternatives like lithium titanate, or LTO, provide very long cycle life and high power but at the cost of lower energy density. For cathodes, chemistries such as lithium iron phosphate, or LFP, are valued for safety and long life, while lithium cobalt oxide, or LCO, provides very high energy density but lower stability. Nickel manganese cobalt, or NMC, offers a balance of performance, while nickel cobalt aluminum, or NCA, is used where very high energy density is required. Geometrically, lithium-ion cells are produced as cylindrical cells like the well-known 18650, as prismatic rectangular cells, and as lightweight pouch cells. Each format and chemistry provides trade-offs in safety, cost, energy, and power. With so many chemistries and formats, there is no single, best, lithium-ion battery. Instead, the optimal design depends on the application's priorities. For example, electric vehicles may prioritize energy density to maximize driving range, while grid-scale storage systems value long cycle life and safety. Portable electronics, on the other hand, may prioritize compactness and lightweight design. The diversity of chemistries, such as LFP, NMC, and NCA, illustrates how the industry is evolving to meet different needs. This optimization landscape shows a maturing and innovative industry that is capable of tailoring solutions for nearly every energy storage challenge. In comparing lead-acid and lithium-ion batteries, key components of lead-acid batteries are the casing, cathode, and separators. Unlike lead-acid batteries, lithium-ion batteries have a more compact design, which enables greater energy density. Lead-acid battery, typically used in automobiles and backup power systems. Its internal structure consists of lead plates, sulfuric acid as the electrolyte, and a separator. Venting holes are also important for gas release. On the right, we have the lithium-ion battery, found in modern electronic devices and electric vehicles. This battery comprises a graphite-based anode, a lithium-containing cathode, a separator that allows ion passage while preventing short circuits, and a liquid electrolyte that carries lithium ions. The key differences between these two technologies dictate their energy density, weight, and applications. Solid-state batteries are considered one of the most promising next-generation technologies. Unlike conventional batteries that use a liquid organic electrolyte, solid-state batteries use a solid material, often ceramic or polymer, as the electrolyte. This design eliminates the need for a separate separator, because the solid electrolyte itself prevents short circuits. It also dramatically improves safety, since solid electrolytes are non-flammable. Solid-state batteries have the potential to offer much higher energy density, enabling longer runtimes in smaller and lighter packages. However, challenges remain. Production costs are currently very high, and scaling up mass manufacturing is difficult. Still, their potential makes solid-state batteries one of the most exciting areas of research and development today. Flow batteries represent a completely different approach to energy storage. Instead of storing energy in solid electrodes, they store energy in liquid electrolytes held in external tanks. These electrolytes are pumped into a reaction chamber where charging and discharging take place. The amount of energy the battery can store depends on the size of the tanks, which means flow batteries are easily scalable for large applications. They use membranes to allow ions to pass between tanks while preventing short circuits. With lifespans exceeding 10,000 cycles, flow batteries are extremely durable and ideal for grid-scale storage and renewable energy integration. Their eco-friendly design and independent scalability make them a strong candidate for the future of sustainable energy systems. Sodium-ion batteries work on similar principles to lithium-ion but use sodium instead of lithium. Because sodium is far more abundant and less expensive, sodium-ion batteries could provide an economical alternative for large-scale energy storage. In these batteries, the anode typically stores sodium ions in carbon-based materials, while the cathode releases them from sodium transition metal compounds. The electrolyte is a sodium salt solution, and separators keep the electrodes apart while allowing ion flow. Although sodium-ion batteries have lower energy density due to the larger size of sodium ions, they are attractive for stationary applications where cost is more important than compactness, such as renewable energy storage systems. Nickel-cadmium batteries were once widely used and are still employed in some specialized areas. They deliver high discharge currents and can operate reliably across a wide temperature range. However, they suffer from what is known as the memory effect, where the effective capacity decreases if the battery is not fully discharged before recharging. Another major drawback is their environmental impact, as cadmium is a highly toxic heavy metal. Despite these disadvantages, NiCd batteries continue to be used in aviation, power tools, and emergency lighting systems due to their robustness and reliability. Nickel metal hydride batteries were developed as a safer and more environmentally friendly alternative to NiCd. Instead of toxic cadmium, the negative electrode is made from hydrogen-storing metal alloys. NiMH batteries offer higher energy density, longer runtimes, and minimal memory effect. They are safer for the environment and easier to recycle. These batteries are commonly used in cordless tools, portable electronics, and especially hybrid vehicles, where their balance of cost, performance, and safety makes them an excellent choice. Although lithium-ion is increasingly replacing NiMH in many applications, they still play an important role in energy storage. Different battery technologies can be compared by looking at key parameters such as energy density, cycle life, environmental impact, and cost. Nickel-cadmium offers durability but suffers from toxicity. NiMH improves safety and energy density. Lithium-ion provides the best balance of high energy density and long cycle life but comes at higher cost. Lead-acid batteries are cost-effective but heavy and less efficient. Solid-state batteries promise extremely high energy density and eco-friendliness but remain expensive and hard to mass-produce. Flow batteries, while having lower energy density, excel in lifespan and scalability for grid-level storage. These comparisons highlight that every battery type has strengths and weaknesses, and the choice depends on application priorities. To summarize this module, there is no single perfect battery. Lead-acid and VRLA remain cost-effective and reliable for many traditional uses, though they are heavy and have shorter lifespans. Nickel-based batteries provide rechargeable options, with NiMH being safer and more efficient than NiCd. Lithium-ion dominates in consumer electronics and electric vehicles due to its high performance. Solid-state batteries are emerging as a next-generation solution with great potential, while flow and sodium-ion technologies are particularly promising for large-scale renewable energy storage. The diversity of these technologies shows how innovation in batteries continues to drive progress in energy storage. Thank you for following the types of batteries. We have explored traditional and modern battery technologies, compared their advantages and limitations, and looked ahead to future solutions. Now, it is your turn to test your understanding with the questions provided, and to think about how each battery technology might be applied in different real-world scenarios.